Hello, it's Scott Manley here. Almost 30 years ago, NASA dropped a spacecraft into Jupiter, an atmosphere probe, which was going to actually analyse the atmosphere of Jupiter on its way down. Now, at the time, we thought that Jupiter would closely match what the original stellar nebula was, and we would learn all sorts of things about this. At the time, I was an astronomer and I had no idea of how difficult this was. The more I learn about this, the more I realize that this was a minor miracle performed by NASA. You may have heard recently that NASA's been having trouble with the heat shield on Artemis. It returned from the moon, it survived, but it had big chunks that had spalled out of it, out of the Avcoat heat shield that had been used. And this is a material that was derived from the Apollo era heritage. It had to have some changes to it due to modern technology, changes in the supply chain and stuff. And it didn't perform as expected. What happened was apparently there was gas that would get trapped and that would expand and then cause chunks to spall off. Now they think they've solved this problem, but that was for a heat shield returning from the moon at about 11 kilometers per second. This is a heat shield which had to go into Jupiter, and its entry velocity would be 47 kilometers per second. If you know physics, kinetic energy goes as velocity squared. So this is a many, many times higher energy. When I tried simulating these conditions in Kerbal Space Program Realism Overhaul, even with physics cheats enabled that made the heat shield invulnerable and stopped joints breaking, it still broke off the rear heat shield just because it was so outside the range of physics that this game engine can handle. The real entry recorded peak temperatures of 15,000 Kelvin. That's 2.5 times the temperature of the surface of the sun. The peak heating was 30 kilowatts per square centimetre. Maximum G loading was almost 250 Gs. But the NASA engineers had expected this. They had overbuilt the heat shield, and the spacecraft made it through and then began a slow descent into the atmosphere. Lasted almost an hour, descending hundreds of kilometers underneath the Jovian clouds. And so I want to go into how NASA achieved this minor miracle, how they got the spacecraft onto the correct course, how they kept it stable, how the heat shield survived, and of course, what they found out when they descended into the deepest atmosphere known to humanity. So the Galileo mission emerged in the 1970s as a logical next step after Voyager, which had flown past Jupiter and provided us amazing views, but also had revealed a number of new mysteries about the giant planet and its accompanying moons. Galileo was designed not to just fly past, but to actually go into orbit and spend years mapping these and investigating them. Previously, they had also flown an atmosphere probe, or a set of atmosphere probes, into Venus, the Pioneer Venus multiprobe. Now that was an interesting mission because it represented two separate launches of an orbiter and the multiprobe bus, and then that multiprobe bus would drop 4 separate atmosphere probes into Venus, which would have to relay all their data through the orbiter. So this required a lot of coordination between multiple spacecraft launches. For Jupiter, however, they simplified this to a single spacecraft, which would have to be the orbiter and the atmosphere probe carrier. That meant that it would release the probes several months ahead of the actual encounter, and then the parent probe would have to adjust its orbit to miss the planet, and after performing the relay of the data from the spacecraft, from this atmosphere probe, it would then have to go into orbit around Jupiter. And the probe itself would be heavily derived from the Pioneer probes. They were approximately the same shape, with the heat shield being a sphere that expanded into a cone. The Pioneer largest probe was 1.5 meters in diameter, but the Jupiter probe would only be 1.25 meters. The spacecraft that was inside with all the sensors and probes, they would have a broadly similar set of instruments, although obviously the ones on Galileo would be more advanced. But the real difference would be the heat shield. On the Pioneer probe, the forward heat shield at the thickest point was about 1 centimeter thick, while on the Jupiter probe, the heat shield at its thickest point would be 15 centimeters thick, and that meant that the heat shield added a lot of mass. While the Pioneer probe was about 20% larger than the Jupiter probe, its mass was about 10% lower. Overall, the Jupiter probe would mass something like 340 kilograms, half of which was that heat shield. Obviously, it needs that extra heat shield thickness because of the massive disparity in the entry velocity. And a lot of smart people out there are wondering why the entry velocity was only 47 kilometers per second, because Jupiter's escape velocity is 59.5 kilometers per second. So how did something fall in and arrive slower than its escape velocity? Well, the entry trajectory was designed to go with the rotation of Jupiter, which is very fast, and it subtracted about 12 kilometers per second just because it was rotating with the planet. And incidentally, because the atmosphere of Jupiter is hydrogen and helium, it has a very high speed of sound. So sometimes you'll see this speed quoted as Mach 50, which makes it sound way slower than it actually was. Now, the probe had to survive on battery power alone, and it would be released in July of 1995 and only enter the atmosphere in December of 1995. So it had to survive all that time on a minimal power supply. It would have a clock that would only wake it up just in the moments before it hit the atmosphere so that it could start establishing its communication with the parent spacecraft. And it had enough battery power to keep it working for about an hour. That was estimated to be the amount of time it would survive before it descended too deep into the atmosphere and was crushed by the pressure. Attitude control was entirely passive. It was spin stabilized, which meant that the Galileo mothership had to spin at the correct speed in the correct orientation when it released the probe, so that 5 months later, when the probe entered the atmosphere, it would already be in the correct attitude for atmospheric entry. The Galileo spacecraft, incidentally, has an interesting design where the bulk of the spacecraft is actually designed to be spin stabilized because it has these like sensors out on booms which can rotate through and sense things like magnetic fields and plasmas, and that's good for that design. But for the cameras, those needed to be kept stable, so there is a stabilized platform with the sensors, which means there has to be a bearing between these two sections of the spacecraft that allows the free rotation but also transfers power and data. And the probe would actually be attached on the non-rotating section. So during the probe release, they had to actually allow that section to spin up so it could rotate correctly and then despin it for later in the mission. Also, the engine which was used for orbital insertion around Jupiter, that was underneath the probe, so they couldn't enter orbit around Jupiter if the probe failed to release. And finally, there was one unintended feature which had a big effect on the mission plan, and that was the fact that Galileo's primary high-gain antenna remained jammed and did not unfold. So the spacecraft was stuck without any high-bandwidth communications to Earth. It could actually communicate much of the data only at 10 bits per second. That's a little more than 1 letter per second. Now, fortunately, there was a tape recorder on board which would allow them to collect the data quickly, store it, and then slowly trickle that back to Earth. Otherwise, they would have lost most of the probe data. But then, as they are on approach to Jupiter, they have a problem with the tape system, and they are really worried that they may lose this at a critical moment. Now, they figure out that they can actually get the tape to move by adjusting some of the software to try kind of roll over sticky spots in the tape, but they are very worried that if they use this too much, they will lose the tape permanently, and with it, the potential of gathering atmosphere data. And so they make the decision that they are not going to use the tape prior to recording the atmosphere data. And this means they're going to miss a critical encounter. The one close flight past of Io is not going to be recorded. See, the thing with Io is it's close into Jupiter, it gets a lot of radiation, so you don't want the spacecraft down near Io very often. And for the orbital insertion, there are dynamical advantages of being as close to Jupiter as possible, as deep inside the gravity well to amplify that engine. So they were going to make one close pass to get that orbital insertion, and that meant they could fly by Io, get some really cool pictures, and then never go close to it for the rest of the mission. But they chose to prioritize the atmosphere probe data because that was a one and done event. That was hardware. There was possibilities that they might fly close to Io in the future if the mission was allowed to continue past its original schedule. So now we get to the big day, December 7th, 1995, about 10 p.m. Zulu time. That is when the probe begins entering Jupiter's atmosphere.
Now, the entry was expected to begin about 1,000 kilometers up. Up above what? Because, of course, Jupiter's atmosphere just sort of continues smoothly downwards. There's no surface, there's no sea level. Well, the arbitrary 0 point that they chose was where the atmospheric pressure reached 1 atmosphere, the same as the planet Earth. For much of the descent, there's going to be no contact with the probe because, of course, it can't beam radio transmissions out through the plasma sheath that it's generating as it descends through the atmosphere. So for the first 4 minutes, we do actually have scientific data because it dumps it later, but the sort of T0 on the data logging actually starts, about 4 minutes into the descent. During the initial part of the entry, the science that can be done is very limited. It can really only measure the acceleration of the spacecraft due to the atmospheric drag. The science package actually had 4 different accelerometers that covered different range, because when they were in the thin upper atmosphere, they would be micro Gs, and during peak deceleration, it would be hundreds of Gs. So for the first couple of minutes after logging starts, we do see a small amount of drag from the atmosphere, but the space probe's velocity will continue to increase because Jupiter's gravity is 2.5 g and it's more than enough to beat the drag. But 2 minutes after the logging starts, we begin to see the velocity decrease. 4 seconds later, the deceleration is 1 g. About 10 seconds after that, it's 10 g. Another 10 seconds, it's 100 g. Over the next 8 seconds, the G loads continue to rise. It is dissipating 20 gigawatts of power. The G loads peak at 230 Gs, and then very quickly they begin to drop off. 10 seconds later, the G loads drop below 100. Another 15 seconds, it's below 10. The entire process takes about 100 seconds in total, but the majority of the velocity is dissipated in around 20 seconds around that 230 G peak. And when the data finally got back to Earth and was analysed, we realised that the spacecraft had almost not made it through. The heat shield contained sensors that would show how far the heat shield had been burned away, had ablated. And the initial designs had gone through a lot of process. They built special facilities to analyse this very extreme re-entry environment, and that's where they had got the thicknesses of the heat shield and optimised around this. But when the data was actually analysed, we understood that we'd got it wrong. There was more material lost around the conic section than there was at the nose. They lost 4 centimeters of heat shield, and they only had 5 centimeters of heat shield to work with. Prior to entry, the heat shield massed about 160 kilograms. It probably lost about half of that. It's now understood that the ionization environment was misunderstood, and the hydrogen and helium would interact under these shocks to generate more light than had been initially expected. So having survived the heat of re-entry, it would soon be time to jettison the heat shield and have the probe itself descend into the atmosphere under a parachute. This would expose the sensors and allow the real science to happen. And this was supposed to happen by the time they reached an altitude where the pressure was like 1/10 of an atmosphere. But due to yet another technical glitch, this only happened 53 seconds late. The parachute deployment process used a pair of G switches. The first one would trigger when it reached 6 Gs and then turn off once it dropped back below 4.5 G, and then there was a high G version that would trigger at 25 G and then disable at 20 G. So these two would be wired into the computer, and the computer would measure the times when these switches turned on and then turned off, and from that it could figure out when the spacecraft was moving below the speed of sound and it was safe to deploy the parachute. But somewhere during the assembly process, somebody had got their wires crossed, and the high G connection was going to the low G system. So what happened was the high G signal triggered first because it would trigger at 6 Gs, and the computer then saw that the high G signal had triggered and the low G one hadn't, so it then assumed that the low G system was broken and used this high G signal that was being triggered by the low G values to then extrapolate when it was below the speed of sound. Now you might think something as trivial as getting the wires crossed would have been picked up during the tests. Well, they did actually put it on a centrifuge system and tested these two switches and they passed. So
Apparently, the test system was also miswired in exactly the same way. So it fell an extra 5 kilometers or so before the parachute activated. There was a mortar system in the rear that shot a drogue chute out. When that extended and pulled on the back panel, that itself then came off, and that pulled out the parachute on the probe. And once that deployed, the probe then fell free from the forward heat shield and began to do real science, and also began to upload the science data to the spacecraft which was currently orbiting overhead. So, what were the science instruments on board? Well, you've already heard about the G meters that were used to measure the density of the atmosphere. That's part of the atmospheric structures instrument. Also, on that, they had thermometers and pressure sensors, which were uncovered once the probe was separate. A second instrument that had also been operating during the descent was the energetic particle instrument. That was obviously looking for radiation that was close to the surface of Jupiter. This also worked in parallel with the lightning and radio emission detector, which above the atmosphere was making radio emission measurements of the magnetosphere, but once inside the atmosphere, it was able to detect the radio signatures of lightning. The rest of the instruments only operated once it was inside the atmosphere. There was the neutral mass spectrometer, which would measure the isotopic abundances of various elements. There was the helium abundance detector, which would measure the ratio of hydrogen to helium, and it did this by measuring the refractive index of the atmosphere with extreme accuracy. There was also an instrument called the nephelometer, which you may not have heard of before, but yeah, it is an instrument which measures clouds. It measures particles that you would find in the atmosphere, because of course we expected clouds on Jupiter. Finally, there's the net flux radiometer that wants to measure the heat coming from inside of Jupiter and escaping into space. So it has a rotating sensor that looks down and then it looks up, and it's comparing those to see how much thermal emissions there are in both directions. And finally, there was one other experiment which didn't need any additional hardware. That was the Doppler wind experiment. That would use the radio transmitter on the probe and the receiver on Galileo to accurately measure changes in velocity relative to the two spacecraft. And since we know how fast the spacecraft was moving, or should be moving, you could then reconstruct changes in the velocity of the probe as it was blown around by winds in the Jupiter's atmosphere. So what did this array of scientific instruments tell scientists about Jupiter? Well, it kind of surprised them. I mean, sure, they were looking at very basic things to start with, things like isotopes. They found that the hydrogen-deuterium ratio was consistent with the Big Bang theories, but they found that there wasn't enough helium, and they found almost no oxygen. And that was important because oxygen and hydrogen make water. So why was there no, why didn't they find any clouds here, right? They found the winds actually continued to get stronger as they went deeper down. Like one model had the winds getting as high as 650 kilometers per hour as they descended deep into the atmosphere. Lightning was detected, but it was about 1/10 of what they expected. Now, since then, we've had more information. In particular, Juno has shown that the water levels measured by Galileo were anomalously low. And it's believed that the Galileo probe fell into what's called a 5-micron hotspot. That is, it's a spot on Jupiter's surface which appears to be emitting a lot more infrared radiation in the 5-micron. And this is because it's lacking clouds. So there's basically a hole in the cloud layer that looks down deeper inside the planet to warmer materials, and so that heat is then escaping through that hole in the clouds. There is a set of images which were taken by the Hubble Space Telescope which shows the probe entry site, and you can actually see the dark areas where you would imagine there are holes in the cloud which the probe could have landed in. But you have to understand that Jupiter's atmosphere is kind of dynamic. It's all moving and rotating at different rates. And these images were taken 2 months before the actual probe entry. One really interesting conclusion that came out of the isotope ratios was the noble gases that were found implied that Jupiter had to have formed in a colder environment, and therefore may have formed further out in the solar system and then migrated inwards. And this is part of many planetary formation theories for the solar system. The probe continued to send data for 7 to 8 minutes after its initial entry into the atmosphere.
It would sink slowly, descending to a depth of 160 kilometers, where the pressure was about 23 bar. The radio system shut off largely due to high temperatures, and the probe was probably crushed by around the same time. And while we can't be sure about what happened next, we can extrapolate based upon our models of Jupiter's atmosphere. So about 25 minutes after losing contact, it would be hot enough for the parachute to melt. So the spacecraft would then sink. It would fall, free fall. It would transition into a region where the hydrogen would enter a supercritical state due to its density. So about 40 minutes after the parachute melted, the aluminium would start to melt. But there would be other fragments of the spacecraft that continue to hold together. Titanium would start falling apart maybe hours after that. But there would likely be components such as diamond windows that held together all the way down to Jupiter's metallic hydrogen core. And of course, while the giant planet was gobbling up the atmosphere probe, the mothership continued on its way. It performed an orbital insertion, and then it spent the next few months slowly replaying the data off the tape to send back to Earth in a trickle of bits that revealed the planet in ways we had never known before or since. I'm Scott Manley. Fly safe.